Your attention, please. We will now move to the second presentation for this morning, and it will be a conjoint presentation by my colleague Usef Faghihi and myself. The theme is the modeling of human reasoning with probabilistic fuzzy logic, and the project is to try to improve normatively human decision in complex situations using fuzzy logic and to make probability functions on fuzzy logic. So it starts like this. What is the relevance at the cognitive level of using fuzziness, the cognitive foundation of fuzziness? Much of human cognition is a construction of categories and causal relations between categories. Categories are the basic units of cognition, I would say the building blocks of cognition, and causal beliefs establish relations of dependency between categories. And much of human cognition is to try to identify categories in the world and relations of dependency between these categories. The classical conception, a rationalist, I would say, conceptions of categorization is that human beings use concepts. It's what so many philosophers in the past have told us. And as a concept, they consider that it is a set of necessary and sufficient intentional conditions for belonging to the extension of the concept. That is basically what was called a definition. So when we talk about dogs, we would have a definition of what are the criteria for an object to be a dog. And then when we refer to a dog, we use that concept. Well, many studies have shown in cognitive science that it is not always, and most of the time, it's not the case that human beings use concepts and have precise definitions for the words that they use. And this way, there are many works that show that categorization is much more something like using approximate prototypes without putting that word precise definition. So most of us, we talk about dogs significantly without knowing precisely the definition of what is a dog. Okay, see, for example, the important work of Eleanor Roche in 1973. So we talk significantly of most objects with a vague representation of what they are, with an approximate set of more or less essential properties. So objects, this way, according to Roche, a certain degree of prototypicality. For example, a dog is much more prototypical of a mammal than is a platypus, for example. So fuzzy logic is a very good tool to represent easily that prototypical categorization. Okay. Now, the foundation of probability. Human beings tend to believe in relations of dependency between categories and as relations of causality between a cause and an effect. And since, for example, as I said yesterday, philosophers like David Hume or Immanuel Kant, they showed us that humans tend to see in the succession of events causal relations between a cause and an effect. Okay. Human beings tend to believe in causes for the explanation of past or present events by anterior ones, and for the prediction of future events by anterior ones. And much of what we have done yesterday about abduction was based on that presupposition. These causal beliefs rely on our long-term memory and are necessarily uncertain, as abduction is uncertain. So much work in cognitive science has shown that spontaneous explanations and predictions use approximate and qualitative probabilities. See, for example, the theses of Oxford and Chater we were talking about a few minutes ago, Patrick, and same with David Over and Jean Baradin was talked just a few minutes ago with us. The conclusions of causal reasonings are often determined by such probabilistic estimations. For example, we often accept or refuse the conclusion of an MPP or a MTT according to our estimation of its empirical probability. So, seeing that, some of us, some logicians, computer scientists, we said, well, why not try something like probabilistic fuzzy logic? And that's what Usef and I worked on. So given that human categorization and establishment of causality are usually approximate and qualitative, we can improve these cognitive activities and make them quantitative and more precise using non-classical logics. As we will see, fuzzy logic can do the job for categorization, and probabilistic logic can do so for causal beliefs. So usually, fuzzy logic treats ontic imprecision, while probability treats epistemic imprecision. So this talk will show how we can apply probabilistic logic to fuzzy logic in order to produce probabilistic fuzzy reasoning. Such probabilistic fuzzy logic can so improve human explanations and decision-making, making them more precisely and nuanced. For example, in medical diagnosis, it's a fictive example. Given the symptoms of our patient, the patient has a 0.7 probability of having a 0.2 cancer, that is a cancer in early stage. And for example, this corresponds also these symptoms to a probability of 0.2 of having a medium elaborated developed cancer, say a 0.5 cancer. Okay. So some references. There are other ones like the book of Buckley, published at Springer Verlag. What I have done with Usef Faghihi and also other collaborators in more recent years. And I would say that in classical propositional logic, the semantics goes as follows. You have a syntactic expression like P or Q. You have functions of interpretation that make the statement, the syntactic statement, true or false, and events in the domain of reference. So this way, we can say that the syntactic expression P or Q is true or is false, given what happens in the domain. If at least one of the two events is in the domain, then the sentence is true. And if none of the two sentences is in the domain of reference, none of them is the case, then the sentence is false. So a formal semantics contains a function of interpretation of the syntactic expression depending on the events that occur in the domain of reference. Okay, classical logic contains only two opposite functions of interpretation, T and F, or 1 and 0, and its domain is a set of coexisting events that are totally and separately present in it. Okay, now let's go to fuzzy logic. What happens with fuzzy logic? You have expressions like P or Q, like in classical logic, but the function interpretation are fuzzy valuations of P or Q, and this allows to treat of events that are more or less in the domain of reference. Like, for example, a platypus that is more or less a mammal. Okay, so in fuzzy logic, the semantic model is more complex than the classical one. The interpretation functions provide truth values that belong to a set of infinitely enumerable rational fractions in the closed interval of 0 and 1. And all the rational fractions between 0 and 1 are possible. The domain of reference contains events that are more or less the case, the world being imprecise, which is a presupposition of fuzzy logic. Objects belong to a set in accordance with a certain degree of membership. That was the thesis of the founder of fuzzy logic, Lofty-Zadie. And this way, we have a membership function that is X belongs to the set A with a certain degree of membership. This way, we have various degrees of prototypicality. For example, we could say of a platypus, typical example of your country, that, well, it can be treated as a mammal at 0.5.
No mammals in New Zealand.
At 0.4, a bird, and at 0.1, a reptile. And when Europeans found platypuses in New Zealand, they came back to Europe, and people thought, even biologists, that it was a joke, that it was not possible that such an animal exists. Well, it is the case. Okay, so we have, for doing fuzzy logic, we have to define fuzzy complements. I won't go in detail in these things. These are things that I study systematically in my doctorate classes. We will now see the usual rules for generating fuzzy connectives. A and B will represent truth values of proposition. And so we have connective, that is C for a complement, I for a conjunction, intersection, U for union, disjunction, and this one for conditional. Okay, and fuzzy complements are such that there are fuzzy complements that behave like what we have in classical logic. That the complement of A is 1 minus A. For example, if an animal is at 0.4 a bird, then it is true that it's at 0.6 not a bird. 1 minus 0.4. Okay, and there's an axiom of limit conditions that the complement of 0 is equal to 1 if complement of 1 is equal to 0. There is a monotonicity function. The complement can be a continuous function and involutive, which means that it's the law of double negation. The complement of A is equal to A. Okay, and property C1 and C2 are necessary conditions for having a complement, but C3 and 4 are not necessary, can be absent in weaker complements. So in fuzzy logic, we can have the classical interpretation of the connective, and we can have also a weaker interpretation of the connective. So we can have real negations like the ones we have in classical logic, and weaker complements, weaker negation. The conjunctions are usually called T-norms. That is the family of fuzzy logic conjunctions. And this, we can estimate the T-norm as a standard. So this weight will be the minimum between value A and value B. For example, a proposition that has a truth value of 0.6 in conjunction with a proposition that has a truth value of 0.3, well, their conjunction is the min, that is 0.3. Okay. It could be calculated also as a algebraic product. So the truth value of the conjunction between A and B is the product of the two truth values. It could be also the bounded difference, that is the max between 0, so you make sure you don't go lower than 0, or the sum of A plus B minus 1. If this is superior to 0, no problem. If it is inferior to 0, then you stick at 0, because the most important value is 1, and the lowest one is 0. Okay, and you can have drastic conjunction. That is, the value of the conjunction is equal to A when the value of B is 1, and it is the value of B when the value of A is 1, and otherwise it's 0. This means that when one of the two proposition in conjunction is not totally true, then the value of the conjunction goes to 0. Okay, only the standard T-norm is idempotent, and the others are sub-idempotent. So we can see different axioms on the fuzzy conjunction, the limit condition, monotonicity, commutativity, associativity, and when we analyzed the different kinds of fuzzy logic, well, we decided that a real conjunction necessitates these 4 properties. And there are 3 others that are properties that characterize weaker conjunctions: a continuous function, idempotence, and strict monotonicity. And axiom 1 to axiom 7 are in standard T-norms, and the 3 others, 5, 6, and 7, are properties that belong to weaker conjunctions. Okay. Sorry, it's the opposite. When you have 1 to 7, you're in standard T-norms. And when you have only the 4 first and not the 3 last, it's weaker T-norm. And I would say falsification not only of the truth values, but also of the meaning of the connective. Same thing for the disjunctions. I mean, there is a standard way of defining the disjunction. When a proposition has a truth value of 0.4 in disjunction with a truth value of 0.7, then it's the max that wins. That is, the truth value is 0.7. And you can calculate the algebraic sum, which is another form of disjunction. That is the value of A plus the value of B minus the value of the conjunction. And you can have also the bounded sum and the drastic union. And this way, this is the result of this one is a higher truth value. This when you go to this, from this one to this one to this one to this one to this one, well, the truth value goes up. And this, for example, and the last one, and the drastic union, when the truth value of A is the truth value of B is 0, then you go to the truth value of A. When the truth value of A is 0, you go to the truth value of B. And otherwise, the truth value resulting is 1. Okay, so only the standard T conorm is idempotent. The other ones are super idempotent, like the conjunctions were sub-idempotent. Okay, and there are axioms that correspond to the ones that we had for this for the conjunction. The disjunctions are T conorms. You have a limit condition, monotonicity, commutativity, associativity. And so logicians thought that, well, you need commutativity and associativity to consider a conjunction as a real conjunction. And it is the same for a disjunction. Without these properties, it would not play the cognitive role of a disjunction or a conjunction. These three properties, idempotency, continuous function, and strict monotonicity, are not necessary for having a disjunction. And this way, they are present in standard quasi disjunctions, but they are not present in weaker forms of fuzzy disjunctions. Okay. Now, this way we have pairs. That is, disjunction and conjunctions are pairs. The min goes with the max. The min of the conjunctions goes with the max of the disjunctions. The algebraic product goes with the algebraic sum. The bounded sum goes with the bounded difference. And the drastic conjunctions goes with the drastic disjunction. This way, each pair of conjunction and disjunction in a fuzzy system is such that they are dual connectives. That is, you can define the disjunction by the conjunction and the conjunction by the disjunctions, making affirmation of the negations and the negations of the affirmation. So you have dual pairs. And having dual pairs, you have distributivity. So each one of the two connectives, the disjunction is distributive on the conjunction, and the conjunction is distributive on the disjunctions. These fuzzy logic constitute not a Boolean lattice. They constitute a distributive lattice. A distributive lattice is a substructure of a Boolean lattice because it doesn't have a basic property of Boolean lattice, which is it does not have complementarity. That is, the conjunction of A and not A is not equal to 0, is equal to 0 or higher than 0. And the disjunction of A and not A is not equal to 1. It's equal to 1 or lower to 1. And the classical case is when it's equal to 1 and when this one is equal to 0. But all the fuzzy cases are such that the conjunction is higher than 0 and the disjunction is lower than 0. Okay. And this way we can generate families of conditionals. And I will talk of 16 families of conditional because each conditional can be defined according to one of the 4 definitions of the disjunction and the conjunction. So there are 4 kinds of conditionals here, 4 kinds here, 4 kinds here, and 4 kinds here. Okay, how do we define the conditional? Well, the conditional can be defined as not A and B, as we have seen in the earlier presentation this morning. It could be defined as true whenever the truth value of A is not higher than the truth value of B. It could be defined that we have not A, row 3 and 4 in classical logic of the truth value, or A and B. So this way we never have A and not B. Another way not to have A and not B is to have B or not A and not B. So this way we will never have A and not B. So these are 4 ways for defining a conditional. And each family, as I say, each of these definitions can be coupled with one of the 4 definitions that we have seen about the disjunction and conjunctions. So this means there are 16 ways of doing an inference using one of the 16 definitions of a conditional. And classical logic, all these rules are valid. Combining each of these 4 formulas with 4 pairs of rules for generating a conjunction at disjunction. We obtain 16 inferential rules, 4 for S, 4 for A, 4 for QL. QL is quantum logic conditional, and 4 for the fourth. That has no other name than the fourth. I call it the fourth because I don't have much imagination. Axioms on conditionals. Wow, this is exciting. This axiom could be present, monotonicity of the first argument. The second could be present. The third one, dominance false. That is, the results of the conditionals is always equal to 1 when the antecedent is false. Neutrality of true. When you start with true, the resulting truth value is the one of the consequent, never the antecedent. Reflexivity. Does A implies A? Well, if it's true, you have reflexivity, but in some fuzzy logics, you don't have it. Exchange properties, limit condition, contraposition, that is the law of double negation, and continuous function. Only axioms 2 and 4 are shared by each of the 16 systems. Okay, very exciting. Some effects on cognition. Standard fuzzy logic is a generalization of classical Okay, I'll try to go a little faster. Standard fuzzy logic is a generalization of classical logic to infinitely denumerable truth values while keeping the classical meaning of the connectives. But non-standard fuzzy logics do not only fuzzify the truth values, they also weaken or fuzzify the meaning of the connectives. Classical logic is the less fuzzy system contained in every fuzzy logic, a subset such that the belonging of an object to a set is equal to 1 or 0. Okay. The difference between the essential and indispensable properties of fuzzy connectives can help to understand the connective function of these connectives in various reasoning contexts. For future research, there is a descriptive question that is not yet answered, and I will try to answer in future works, and a normative question. Which fuzzy rules for the connectives are at work in different reasoning contexts for human beings? And the other one, the algorithmic question. And the computational question, which fuzzy rules for the connectives should be used to assist more efficiently human decision in different decision contexts? Okay, now some brief considerations on probabilistic logic. The truth values in probabilistic logic belong, like in the fuzzy logic, in the rational interval of 0, 1, like in fuzzy logic. The conclusion of the inference is uncertain. This is epistemic uncertainty versus the fuzzy logic, in which it is the state of the world that is uncertain. To deal with uncertainty, conclusions, probabilistic logic replaces the classical conditional by conditional probability, as we have seen in the presentation of Maxime and Jean. Classical propositional logic, in this sense, is the simplest subset of probabilistic logic. That is the one we have when all the conditional probabilities are equal to 1 or 0. Classical logic is the simplest probabilistic logic. So how does the semantic work? We have functions of interpretation that are, what is the probability of the expression P or Q to be true? So we have a domain of reference in which it should contain events according to a certain probability of being there according to our knowledge, which is different from the other semantics. And the basic rules are these rules. The probability of not A is 1 minus probability of A. That's how we define negation. For the disjunction, when the two events are exclusive, that is when the probability of A and B is equal to 0. The probability of A or B is the sum of the two probabilities. And when they are non-exclusive, well, we have the probability of A plus the probability of B minus the probability of their overlap. And then the probability of conjunctions, well, when the events are independent, it is the product of the two probabilities, but when they are dependent, it is the probability of the first multiply the probability of the second given the first. Okay, and because disjunction and conjunctions are defined with different constraints, as you see, different constraints, there is no distributivity between these connectives. Okay. And we have the law of conditional probability that we have seen in many of the presentation that we had in this school. So I'll go to the next slide. And the Bayesian law is such that the probability of an hypothesis given a new evidence is the former probability of the hypothesis multiplied by the likelihood of the evidence given the probability, given the hypothesis, divided by what we call the marginal probability, that is the probability of the new evidence. Okay. Unlike classical logic, probabilistic logic is non-monotonic because of Bayes' law. New information can change the truth value of the conclusion. Probabilistic logic is a good tool for modeling learning. While in spontaneous reasoning, probability statements and corrections are approximate and qualitative, Bayes' law can help to make such statements and corrections more precise and quantitative. And that was the objective of what I've done with Usef. So the superposition of probability and fuzziness. Fuzzy logic and probabilistic logic are non-classical, non-Boolean for different reasons. Fuzzy logic is not complemented, as we have seen. Probabilistic logic, as we have seen also, is not distributive. So we cannot integrate them in new probabilistic fuzzy connectives, but we can superpose them with probabilistic functions of relative dependence over fuzzy functions about objects and events.
You went over.
Okay, and we will see now an example. The oncologist would prescribe chemotherapy if the patient has more than a 0.7 probability of having a 0.2 cancer or more than 0.3 probability of having a 0.5 cancer. So this is how we will move to the second part. I'm sorry, I've been a little long. The second part of the presentation, my colleague and collaborator, Usef Faghihi, will present an example of computational implementation of probabilistic fuzzy logic that we achieved. So that's it. Sorry. Let's move with Usef. Okay. I always want to explain too many things in the same presentation.
I always learn that.
Just a second.
How many of you guys, you're familiar with causal inference? Oh, good.
Pierre, of course.
Pierre is not counted. A little bit. Okay. Two things before I start, guys. I just arrived from Europe, so a little tired. And the second is that I tried a lot to make fonts the same in every slide, but it didn't work. Sorry. Hope it doesn't. Just focus on I guess it here too.
I have tried to explain to my family doctor probabilistic fuzzy logic, and she enjoys it. And I feel safer at my annual visit. Doctor.
Okay, so for this part of the presentation, what I'm going to do is I will explain very briefly about causal inference and one of the problem in causal inference and how fuzzy logic can help with to solve this problem. Okay, here we have for some people who knows the causal inference problem, they know this example that let's say we have this observational data. We see that the smokers, they are more probable to have cancer. Okay, so they have higher cancer incident in average than the people who are not smoking. But the big problem here is this one. Okay, so usually what we see the observational, we see the treatment, which is smoking, and we saw that okay, this caused cancer. Now, so you can say, oh well, let's say that there is a cancer gene here that we have no idea about it. So this guy is gonna influence the treatment, which means that the guy who's smoking, he might have this cancer gene, and at the same time the outcome. So these guys have more cancer. So you see here we have two routes, one from here to here, and this one from here. In many problems, such as industrials and everything, you can see these confounders are always there and they mess up the result. So here we go with this cancer problem. So I just show you do, it means that I'm giving treatment, otherwise not. So the treatment is binary, just for your knowledge. And this is the outcome. So outcome for an individual, when we intervene, we put the treatment, we give the treatment, we have this potential outcome for this individual 1, and for the guy who didn't smoke, so 0. I said potential outcome, I didn't use outcome because there is a difference. So what is the difference? Here you see one person, the fundamental problem of causal inference is that one person, it cannot be in 2 states at the same time. I cannot be a smoker and not a smoker at the same time, right? So if I'm a smoker, it's a factual, otherwise it becomes counterfactual. Okay, if I don't smoke, I know that I'm not a smoker, but I don't know what would have happened to me if I was a smoker. So we use counterfactual, and that's the reason we're using the potential outcome instead of outcome. Okay? Well, so the causal effect is that we are giving the treatment subtracted by the same guy. I insist in causal inference, we are always looking for the same person taking treatment, not taking treatment. Okay, so that's the reason we do that. So here is a little tricky. When we have this individual, we apply this mean, expected value or mean, it becomes for whole population. So this one is not equal to this one. Why? Because here we are applying to everyone treatment. We want, I mean, hypothetically, we want to apply to everyone treatment, and we don't want to apply treatment to everyone. So this is not equal with the statistical problem, which we compare the subgroups that we apply the treatment, we don't apply the treatment. So causal inference try to solve this problem. Is it possible to go from here to here? I mean, these two becomes equal. Under some assumptions, yes. How we do that? Okay, well, I just wanted to also just emphasize a little bit. So this we call it in causal inference backdoor. Why? Because people with the smoking gene are more likely to smoke, okay, and at the same time, these people have more likely to have cancer. Okay. So what we do here, please ignore this part. The bias that always we have in data, how we take care of them. We take the people who are in control, and then here's a little trick. The guy who's smoking, we would like to hypothetically say that if these guys hadn't smoked, okay? So here, by subtracting these two, we try to find the problem. So in causal inference, we have 2 assumptions. Well, actually, we have more, but 2 important. What we say is that the potential outcome of the guy receiving treatment and not the receiving treatment is independent of treatment. Okay, so it means that it doesn't important this guy is received treatment or no. If we have all information about this guy, for example, the age, anything. So there is no hidden thing here. So if you have this one, the ignorability and the consistency, for example, the observed outcome matches the potential outcome here. If you have 2, we can easily make these 2 equal. Okay, we can get to this one. Okay, now someone from Mr. Pearl, the Professor Pearl, who is from UCLA, who came with these 2 calculus. He solved this problem like this. Okay, here we have this confounder. What he says that we take the treatment, we cut all the coming flashes to this treatment, and if we do that, so we are cutting this ambiguity between these 2. Okay, so on the left we have, what do we have? I have the probability of U, probability of T given U, and this one given these 2, right? But if I delete these 2, I'm deleting this problem, right? So I can deconfound this problem. Now, fuzzy logic. Okay, for some of you guys who are familiar with the causal language model, this is stratification. Somehow this stratification, but using fuzzy logic. So in stratification, what we do is that we take population, we subgroup them, and then we compare the groups that can be compared. Okay, but here in fuzzy logic is more, in my opinion, is better because we beat those guys' result. with Serge actually. So we are doing falsification, defalsification, probability. Serge already explained all of this. Basically, so here we have this falsification, for example, for the cancer. You see that for the low, it's here, medium. So one person can be in both. We do the same for gene and we do the same for the output. And then how we detect the bias? When we are falsifying, you see that here we have the smoker and the non-smoker. So you see the difference between these two. So the fuzzy logic is capable of detecting these high-risk subgroups. Okay, so in fuzzy logic, we are having here we have 3, but it can be 5. It can be more than these groups. So we have low subgroup smokers versus non-smokers, medium, and then high. And once we do this, we can aggregate and create a weighting here. Yeah. So in whole, we have the low, medium, and the high. So for the low, we have this risk of cancer, smoking with this U, low, and then medium and high. And this weighting is calculated like this. And we know that usually in fuzzy logic, we have the normalization. So low, medium, all we cancel. Very easy to calculate. Okay. And then these two just we have Gödel norm, and this is one example. We use many different type of fuzzy logic rules. One of them was Gödel norm and Gödel norm. As you can see, we have this minimum. Serge just explained. I'm not going to go through that. So, but just for the defalsification, we are using an aggregation of all of these places. For example, here we have little, we have high, and here we have medium. Here we have high. So you have this aggregation with this. No, well, so fuzzy logic, it doesn't simply ask, do smokers have more cancer? It also asks among people with similar smoking gene risk, does more smoking still increase cancer risk? So basically, we are answering cancer risk from smoking gene biases. And here is, oops. Sorry, I went a little fast, but if you have any questions, if you have time, I can just go through those.
People might have questions for us. You can imagine that we had much fun doing that and hope
Yes.
that the
Yeah.
doctors will use it for the diagnosis of illnesses.
Yes, there's a question from online. So Alexandria says, question related premise is we make an inference based on empirical probability. How is this outweighed by our belief systems that may be rather fuzzy? We believe somewhat strongly, etc., as needed holds. Not sure.
Not sure I understand correctly the question.
Well, I can try something.
Go ahead.
Yeah, okay.
Yes, sure.
Okay, I don't want to take too much.
No, please.
Okay, well, the way I understand the question goes as follows. In probabilistic modeling of a human problem, people try to estimate. They don't know for sure what if event A happens or not. So they try to rely on their beliefs and the evidence that they can perceive in the world to try to estimate the best possible way what is the probability that the event will occur. Like in the case shown by Usef, what is the probability for people to have cancer given their age, given their they have the gene, the smoking gene or not, the tendency to smoke many or few cigarettes per day, and so on. And our standpoint with probabilistic fuzzy logic is that not only our knowledge of the dependencies in the world are based on belief and have to be adjusted given new evidences, according, for example, to the Bayes law that we can apply, but also the things that we categorize in the world are not often sharply distinguish one from the other. So this way we use fuzzy logic to try to understand how much an object has or not such or such property. And then we make a classification of the data. Then I had not enough time to explain it, but you said a word about it. We defuzzify to take a decision. And then, for example, we say when the risk is higher than 0.7, then we apply the chemotherapy or another kind of medicine. And then we establish a probability over the defuzzified classification. Of course, it is not simple, but producing AI programs that can do that, it doesn't replace the doctor, but it helps the doctor to take a more rational decision and with more flexibility. So that is the goal we were trying to achieve. I would say that's about it.
We have another question from Jenny online. Just gonna read
Yeah,
it.
Jenny. Hi, Jenny.
Jenny Brisson says, can you tell us a bit more about non-involutive negations? Do you see context where they would have cognitive relevance, or could it be a bridge too far for the human mind?
Wow. You know why I work with her? She always has a good question. Okay. The involutive negation, that is, the negation of A is equivalent to A. It's the law of double negation. It's in classical logic. It is at work in standard fuzzy logic, because in standard fuzzy logic, we use fuzzy truth values, which is opposed to classical logic, but we keep the meaning, the semantical meaning of the connectives. So we keep, for example, this property of double negation. But there are some fuzzy logics, as I said, that are not only fuzzifying the truth values, but also the meaning of the connectives. So there are some weaker negations in which to negate the negation is not equal to the affirmation. It doesn't go up to there. Someone says, hey happens, the other one says, no, hey does not happen. And someone said, no, not A does not happen. Is it coming back to A? Well, in classical logic and in standard fuzzy logic, yes. But in weakened definition of negation, well, it doesn't go exactly back to the affirmation. Now, the big question, and I hope, Jenny, you will work with me on that. What are the cognitive contexts in which use the Gödel definition of the fuzzy connective? Is it approximately spontaneously used by human beings? We don't know. And why we don't know? It is because psychologists, as I said to Patrick, psychologists work on algorithmic procedure. What are the de facto procedures that human beings use? And logicians are the ones who work computationally, and the cognitive scientists also. That is the one who try to model what is the connectives and the mental operations that are at work in a given situation. We need to join these things. This is why we have something like a doctorat en informatique cognitive. This is why we have Institut des sciences cognitives. And this is why we put together psychologists, linguists, logicians, computer scientists, and so on in the same meetings. And I don't have any precise answer to your question. I think we have to look for it. And I think that we need to make experiments in which we ask people to take into account negations of expressions and negations of expressions, and see where they are ready to consider that the negation of the negation is equal to the affirmation, and where they're not ready to go that far. I mean, human beings, my intuition is that human beings in many contexts, they negate weakly and not strongly, as classical logic tells us. And this way, when they negate the negation, well, they do not go as far as the affirmation. So and I think we can see that in many examples. For example, I say, I believe that the thesis A is true. And my opponent says, no, it's false. And I come back and no, it's false and it is false. And says, do you mean it is true? Well, I'm not going that far. Given that you talk to me about the negation of A, the possibility that A is false, then I'm not totally sure that to be opposed to you goes as far as the affirmation. It happens in our discussions. For example, a Republican is opposed to a Democrat, and a Republican says Trump is the best president that we had in the history of the United States. And the other one, the Democrat says, no, it's false. And the other one says, it's false and it's false. At times, when he's dogmatic, he says, well, it's true. My belief is true. But he could say, given that you gave me some arguments about your critiques of Donald Trump, well, I'm not as sure as I was earlier that he's the best president in the history of our country. It's a weakened negation. I would say, well, to solve an opposition between two opponents in a conversation could go through that weakened form of negation. Very exciting question, Jenny.
I made a mistake. We still have 12 minutes.
Oh,
sorry.
Good.
There were questions from the audience. I think Elise had a question.
Yes, I just wanted to know, I'm interested in belief updating and probabilistic. We often use probabilistic model for belief updating. So I'd be curious to hear, could fuzzy logic be interesting to model belief updating, I guess, especially when it pertains to categories?
You anticipate my answer. I would say if it concerns categorization, I would say so. But if it concerns causality, I think that Bayes' law is a very good tool. I think that what you have presented and the way you implemented it, it shows it well. But there is a cognitive problem that Paul Thager talked about yesterday, is that people in everyday life, they use approximative and qualitative estimation of probability and belief change. And this way, the Bayes' law is a normative tool that is useful to improve our decisions about belief change. But it would probably not be very realistic to consider that the Bayes' law is a way to represent correctly what people not knowing logic and not knowing probability theory do in their everyday life. My standpoint is that people often use probabilistic estimation, but qualitative and approximate probabilistic evaluation. And this way, the tool we developed is a normative tool that helps human beings. We're not saying that people act this way. We're saying, well, using such tools, they will have more rational decisions. They will take more rational decisions. I didn't tell my doctor, well, you do that every day. I just told her, well, try to use these tools and you'll be a better doctor. And she's getting convinced. So I won't change the doctor. Anyway, changing the doctor in Quebec is very complicated. You decide.
There's another my question is, I guess, how would you take that in practice, let's say in the medical field, and how does the falsification process gets applied in practice?
Well, we don't have to say this, but well, this is one of our first work. I mean, the falsification, but with fuzzy logic, that's the reason Serge discussed about probabilistic fuzzy logic. There are some problems mathematically that we try to solve. And And the reason that I discussed for this, for the falsification of data set, you can do falsification. You have columns usually. I guess you're talking about the columns you receive, for example, the information about the patients. Is that your question? So you look at the data set, you can just falsify them and then defalsify them according to their categories. In order to create these categories, I showed you low, high, those stuff. So you can just have some clustering algorithms that it tells you, okay, these guys goes to low, these guys to medium, these guys go to high, and then you apply falsification if that was the question. But maybe another time I can explain the problems that we had with probability fuzzy logic, and we created another causal model that right now is underway by the university. So another time discuss about it. But if you want more information or the things that we have done, you can just send me an email. I'll share with you. It's a real pleasure. And believe me or not, we applied this falsification on many problems, industrial problem, healthcare, many problems. Yeah. Yes.
Can we have an insight? Well, to use the fuzzy logic but some example who the fuzziness gonna be working. Need some example when the gonna be strong.
If I understand correctly, your question is that you want to see where fuzzy logic has problem, right? Yeah. When you are doing falsification and defalsification, you may go beyond number one. Yeah. And we, as I said, we had some solution for that. We wrote some papers about it. It's all. The only thing I wanted, if that's a little clear here, is that these researchers are from UCLA, from Harvard, okay? And what they're saying is that they're deleting completely this connection between these columns. Okay, let's say this is your data set. So what fuzzy logic is doing is that it make it very fine grain. It's not deleting this kind of, because here when you delete that, you're supposed to say, okay, I'm gonna give you 20 cigarettes per day. You need to, and I'll see what is the outcome. But fuzzy logic is really going in fine grain. So there are some algorithms you can say who are the small, who are in medium, or in high, and then you can calculate, you can compare the subgroups. That one big problem in causal inference is how you can really understand how you can compare the groups. Otherwise, you have this problem of confounder, which we don't know what is causing the cancer. Is it the smoking, or is it itching, or is it both?
I have a question online. If
Yeah.
anybody wants. Is there another question here first? No? Okay. I'm gonna go to the question online. This is Jean-Vincent's question, actually. Beyond the carcinogenic aspect, with the cancer aspect, is your idea to add granularity to quantitative statistical methods? For example, comparing the effect of a substance on men and women would require taking into account the age of the participants.
Yes.
If so, how does this differ from the quantitative rigor required in statistical methods?
Because I hided a lot of. There's a big part that we are calling it average treatment effect. But what you're just asking is that adding more variables, it's CATE, conditional average treatment effect.
Right.
So basically, we are adding those conditions for everyone in calculation. But I didn't show that because
Yeah.
I wasn't sure. Yeah.
So you combine the previous fuzzy value attributions to the new ones,
Exactly.
given the new variables.
Yeah.
And there's no limit to that. I mean, you had new variables based on new statistics, and then you had the new falsification of this variable and integrated within the system. And it works because we have rules for the attribution of a disjunction, a conjunction, and all the connectives have a definite have a definition that is clearly stated in the system. And this is the way a logical system works, with nodes and connectives between the nodes and a syntactic and semantic definition of each of the connectives. Yeah. And one of my doctorate students in the doctorat en informatique cognitive has recently defended his thesis on the application of probabilistic fuzzy logic to a case in medicine that is the septicemia, how to estimate the probability of a septic death within 72 hours after septicemia, given that about 1/3 of the patients die within 72 hours, and it's very difficult to make the diagnosis, and it's one of the worst. Can imagine illness, and the rate of deaths, I would say, as I told you, is 1/3 within 72 hours. So it's still a huge problem in medicine. And he applied our probabilistic fuzzy system to the diagnosis of septicemia. And now, since last week, he's a new doctor in our doctorate program. Well, that's about it. So it's 45. Okay. Thanks for your attention. And once again, thanks to Usef, who has done so much in this work.